That's all I got. I know, right?
All right, let's get started.
How are you?
So this is SOS 212.
Pretty good. Always good to hear. Okay.
Hey, Systems, Dynamics, and Sustainability. So this used to be called like kind of the Calculus 2 of the BS in Sustainability. My name is Ted Pavlic. I'll be the faculty member teaching this class this semester. My appointment is split between engineering, sustainability, and actually life sciences. So I do a lot of interdisciplinary work, and all of that work involves modeling, and that's a lot of what this course will be about. So if there's an instructional staff page on Canvas, which will list office hours once they've settled down for both me, and we've also got the TA here, Taha. So we'll both have office hours, at least one a week, and then of course you can also email for appointment. And so if you haven't gone to the Canvas site, so go to the Canvas site. Most everything is under modules, and so pretty much any assignments I give, I'll put under modules, but you can also find them under the assignments as well. So the way, if you need to send me an email, I teach a couple other courses, and then I also do research and things like that, but I want to make sure that I see your emails and give them the right priority. So if you can, try to start your emails with this, with like SOS 212 and the subject, and then maybe like a short example of what you're emailing about, and that will help me make sure that I see your email and it doesn't get lost in a bunch of other emails that would otherwise, that I might ignore because they just kind of look like the spam that I get every day. And so that kind of helps make sure nothing falls through the cracks. If you have a grading question, so Taha will be doing most of the grading for things that are on paper assignments or things that are submitted to Canvas that aren't auto-graded. And so make sure to email him or both of us, but definitely email him, because if you email just me, then I'll end up just checking with him anyway. And so make sure to include him on that. So the objective here is roughly to identify, model, and analyze complex dynamical systems using computer simulation. So you've taken SOS 211, and you were introduced to certain mathematical frameworks, but it might have kind of a mathy class, and may not have completely been clear how that might apply to sustainability problems. And so what we do here is we show you how to take the insights that you gained from 211, but throw away some of the kind of mechanistic stuff about how to actually do the math, and find a way to use computer simulation to do the hard work for you so that you can build these dynamical models and not worry about having to solve them, because the computer handles that for you. So how do we go about going about building mathematical models and worrying less about how we solve those mathematical models? So by the end of the semester, hopefully, you'll do a project that helps you practice this, is that you're going to identify systems appropriate for this type of modeling, and you're going to be able to build simulation models in a high-level language. So you'll be introduced to 2 software packages in this course, but these generalized. There's a lot of different alternatives out there on the market, and then end up parameterizing those to make them look like real-world systems, interpret your output, and communicate your results effectively in the forms of presentations and reports. And so that's kind of what's driving how we put together this course. So prereq. So SOS 211 is a prereq. And so what it would be great is if you can sort of look at these things that are up here, and you're not going to ever have to actually do this math in the course, but it's great if you kind of remember the essence that this math could be done. So for example, as a refresher, this is what's the derivative of t cubed plus 5? Can anybody tell me what or recall how to take that derivative?
You drop the constant, bring the exponent into the front, and then you would subtract 1 correct.
Sure, so then what would the answer then ultimately be? Right, so 2t squared. So I'm going to see if I can bring up the little, oh right, so I'm not in a PowerPoint presentation right now. So if I were to flip over, let's say to here, so the derivative of t cubed plus 5 is just 2t squared. And so that seemed very mechanistic. You just learned how to, to follow some rule. Hopefully by the end of the course, you'll have a more conceptual, kind of visceral understanding of what's going on here. How, if this is the quantity, the number of people that have a particular idea, then this is how many people are gaining in that idea or losing in that idea. So this becomes a quantity that models something in the world, and this becomes how quickly that quantity is changing. And so that's what we'll kind of get at there. So likewise, this integral here, so that was the next one on that slide. So does anybody recall, or could, that you can use this kind of for help, what sort of should show up here on the right-hand side of this one? So this is the last time we're going to do this level of calculus in the course. It's mainly just to get people warmed up to the idea that there is calculus behind the scenes, but we're not going to do it. That this is stuff that ends up being done for us by the computers, but we have to appreciate that this stuff could be done. So does anybody remember how to do these integrals? It's kind of the backwards of this. On that 2 up here, I apologize. Should be a 3. So what do we get here? Anybody? How do you take the integral of 3t? Not necessarily how, but what is the outcome of the integral of 3t squared when you integrate from 1 to x? We're all a little rusty after. Right. Anybody want to take a stab at it? I can wait. Yeah.
Is it 1/3 t cubed?
Well, so almost there. So it feels like there should be some fractions that come up here because you've got this 2 here and all that. But you have to remember there's this 3 out front here. So I like the 1/3 t cubed, but you have this 3 out here, and you find that at least initially it looks like you get just a t cubed out. So if I were to, I can take that 3 out there, and then you said I do 1/3 t cubed. And so this thing goes away, but so this, effectively I can just cancel it out and I just get t cubed back out. But then what do I do with these limits of integration? Anybody? So I've done half of this. This is what we call an antiderivative. So when you see a notation like this that says you've got something here and you've taken the antiderivative, then what do you do with these limits? Yeah.
You would subtract, so it'd be x cubed minus 1.
Exactly. So I might write that as this, and then I would put on the side here x cubed, and then minus 1. And so this is the very mechanistic way to do it, and hopefully by the end of the course, again, you'll have a physical feeling for if I've got a flow rate going into something that starts at 1 and goes, and I'm taking it from time 1 to time x, then this is going to tell me what that quantity is going to be at the end time x. And so we're going to get sort of a feeling for quantities that things are flowing into them and flowing out of them. They've got initial conditions, and then they've got final conditions. And so this whole course is about modeling systems that change over time, given initial conditions, and then trying to predict what their final conditions are and what path they take along that way. And so similarly, if I had something like a simple integral like this one, and this is the last one here, then I know that if something's constantly having something flowing into it, then it is going to rise at a linear rate, and so you end up putting a t in here, but then you evaluate that from -1 to 5, and that gives me 5 minus -1, or 6. And so what these things end up giving for us is they say, well, given I've got certain flow rates, if I were to evaluate those flow rates due over time, then I get to see how much has the system changed, or where is this, and this gives me a hard number. The system started at a particular level and it ended at another level, and all of this integration is going to be done for us by computers, so that all we end up designing is the stuff that goes in the middle here. And we're going to end up designing those actually not by writing out formulas this way, but in most parts by drawing graphs of interactions. And so in this course, we basically are going to focus on breaking real-world systems up into how different components depend upon each other, coming up with really simple mathematical expressions for those tiny components, and then letting the computer group all of those graphical relationships together and form these things and do all of this junk for us and spit out answers like this one. So we can ask, given I have a particular change that I want to make to the city of Phoenix, how is that going to affect water availability in the next 30 years? Well, I'll be able to predict ahead, what water will, how much water will be available in that 30th year. And behind the scenes, it's doing all this calculus. But all we're doing is designing the stuff in the middle. And so that's kind of broadly where we'll end up going by the end of the class. So there's a textbook that goes along with this, and if you've read the syllabus, you can see that this is a freely available textbook in PDF form from the library. So if you'd like to have a hard copy form, you can find it. It should be at the bookstore. It is also the textbook used for at least one other course on campus, IE 477, that's a very similar name, System Dynamics and Thinking, but it's a 400 level course, but otherwise actually follows a relatively similar syllabus as this one. And then if you, this is linked from Canvas, and so if you go to Canvas, you can download each chapter as you need it, and there will be chapter readings that we'll do as we work our way through the book. The book makes it look a little bit like a business book. It talks about strategic modeling and business dynamics, a feedback systems approach. But like we'll see, most of the examples are built around sustainability and ecology, so there's a fisheries example that we'll see throughout the book. So even though it looks kind of like something that would just be used in understanding sort of business strategy, it really is very easy to move it into these sustainability problems. And so find it to be a nice text, and it's nice that we can get it for free, and it's a pretty common one as well. If you're interested, so then there's also software packages, and so these are also freely available. So as early as maybe the end of next week, we'll start using this package called VinSim. It should be installed on these computers, and if it isn't, it will be installed very soon, but then you'll also be able to download it onto your own computers. And so then there's also a web-based program that is kind of an alternative to VinSim. We'll start with VinSim because I think VinSim's better for these particular things that we start drawing in the first part of the course, but as we transition to these other components that VinSim can use, I think sometimes it's more straightforward to use Insight Maker. And so I'll introduce both of you to these, or both of these tools to you, but then you can decide which one you like better for as you move forward with the assignments and with the final project, which I'll get into in a second. And then we'll also dabble a little bit initially just to get our heads wrapped around this modeling stuff using spreadsheets, so using Microsoft Excel, which you've probably seen before, and maybe done even some of the very similar exercises in, say, SOS 101 with logistics growth and things like that using a spreadsheet. So we'll start with those types of examples, build on them, and that will kind of allow us to then segue into these more sophisticated tools. If you're interested in more details, and I put this on the syllabus, these are two other textbooks that I would recommend. So this Modeling the Environment by Andy Ford is largely the kind of ecological the ecological analog to that Moorcroft book that we are using. And so a lot of the examples that I'll use in the lectures actually are borrowed from this book and even in some of the homeworks. And so that's a good reference to have if you really get interested in this. And then a more sophisticated reference is this Dynamic Modeling of Environmental Systems. So both of those are linked in the syllabus, just if you're interested, but they're not necessary at all for this course. And then again, if just to give an example of other tools that are out there, AnyLogic is another very popular competitor to VinSim. And if you were to go online and search for system dynamics modeling, and there's I think a Wikipedia page that lists a bunch of competing products, you can find there's probably at least 100 of these software packages. They're used throughout industry. So if you get trained on one, then it's very easy to port skills to another. And they all have pros and cons, but the fundamentals are all the same. So the fact that there are all these tools out there kind of shows that there is a demand for this. So hopefully you'll come out of this course with a marketable skill as well that you can put on your CV, that you have background in Vincent and Insight Maker, and if you want to, if you really enjoy it, then you can try some of these other packages. NetLogo is the one that you've taken any of the agent-based modeling courses that Marco Jansen offers. He uses NetLogo, and it actually has a system dynamics component involved in it as well. And then there's a bunch of other online resources. These are all linked from the syllabus. So there's a bunch of extra places that you can get help if you'd like it. So the way the course is structured is we will have a midterm, and it's closed book and closed notes, but I'll give you a formula sheet. And we do something which I think a lot of courses don't do, but I will give you a retake opportunity. And so what that basically means is you only even have to take the first midterm, and there will be a totally different midterm, but basically when I make the first midterm, I have another midterm next to it. When I make question one, I form a question one on the second midterm, which to me is identical in difficulty, although different in content. So you get the same length midterm, the same format of the midterm, but about 10 days later you can take that midterm, and I'll give you the highest score of those two. And the way I think I've scheduled it, and there's a tentative schedule that's on Canvas, is that the second midterm is I think the Thursday before spring break. So or maybe the first, one of them is the Thursday before spring break. And so sometimes people want to leave early or something like that. You can choose whether you want both shots of the midterm or only one, and that gives you the flexibility for that. Similarly, for the final exam, it also will give a pre-take in class, like the last day of regularly scheduled classes, and then during the final exam period, the normal final exam period, that's where we'll have the true final exam, which is actually just a retake. So if you're happy with your pre-take scores, then you just don't have to come to the final during finals week. And I give these, typically as Scantron, so there'll be multiple choice exams, but that also means that I try to get you your scores that day, if not the next day, or I could say the next day, if not that day, so that if it comes around finals week, you're trying to decide if you want to get out of town early, then hopefully you'll have your score, and that'll kind of determine whether you really want to stick around for that second shot. So that's how the exams are structured there, and I just want you to know that ahead of time, because sometimes it seems like that takes some of the anxiety out of taking that first exam. Then we've got a couple of assignments. There's about, I think, 5 or 6 of them peppered throughout the semester. Most of these will start in class, and we'll work together and make the first half of it, and then you'll get a couple of days to finish them off. And then you'll upload those to Canvas. There are reading activities, and so I will assign chapters associated with certain lectures, and before that lecture, you're expected to do the reading. And then the night before the lecture, we'll have an online Canvas exercise, which is auto-graded, which just kind of like hits on the key points. And you can have that, usually you can have that kind of up and running along with the chapter, so that you're kind of making sure you're getting all the points that I want you to see. And then for the first 10 minutes of that lecture section, we'll have a paper-based assessment, just to make sure that we've all done the reading and we're all on the same page, and kind of get you thinking so that you're ready to ask questions before we go over the content and discuss that chapter during that lecture. Then we've got these funny things called muddiest points, where at the end of every week, graded for completion, not correctness, there is a short 3-question survey that's due, I think it's due Sunday nights, and so it will be released Thursday after this class is done. You'll have from Thursday to Sunday. And in the first question, I just want you to give me a sentence, maybe, or even a couple of phrases that tell me what you think was the clearest point this week, what you think was the muddiest point this week, and even if everything was clear to you, there's got to be something that you think is like least clear. And then if there was anything that was like particularly interesting you'd like to know more about, then tell me that. And if there wasn't, just say NA. And so I want you to do that every week, and do that Sunday. I'll review those to see if we need to call any audibles. But generally, I think it just helps to kind of reflect upon what we've learned that week. So class participation, we'll kind of go over that. But I take attendance, but I'll see, I kind of drop your low. There's a couple of different drop policies here. So I'll drop your lowest like 5 attendances. So I know that people, every once in a while you have to miss class. And that's okay, and it's only 5% of your grade, over the entire, whatever the 30 visits, and you get to drop 5 of those. So hopefully that gives enough flexibility. And then there's this final project, which we can talk a little bit more about here in a second. So I've kind of already gone over most of this stuff. I will highlight that in the reading activities, I'll drop the lowest at-home exercise and the lowest 2 in-class assessments. The muddiest points, I'll actually drop one of those, because every once in a while you just forget to do a muddiest point. And then the class participation, I'll drop the lowest of those, and lowest 5 of those, and they're just graded for completion. Does it look like you put an effort into telling me what your clearest thing from that week was, what your muddiest thing on that thing was, and if you had anything interesting? The final project, due to the size of the class, it's a group project, and I also think it ends up helping. For this one, as we have, I think, 30 people enrolled right now, to simplify the kind of grading, and this size, I don't want to go any higher than this, but nominally groups of 4 students, there potentially could be groups of 3, but nominally 4. And the idea behind this project is you are going to choose a real-world system you would like to model. It could be some nutrient flow. I think I give some examples here. So it could be the modeling of diffusion of ideas into a society. Why aren't people buying a particular type of light bulb? Or, can we model the pressures to sort of get for the adoption of a particular sustainable technology? Modeling dynamics of waters and reservoirs around a watershed system. Electricity consumption in a major city. Effects of population growth on a number of different things. The abstract from social justice to the more concrete, like energy, how these things relate to climate change, etc. It would be great if they're sort of sustainability related, but I kind of just really want you to practice the modeling concept. So even if there's not really that close of a sustainability relationship, that's okay. It's just it'd be great if you could find one of these. And so with your group, you pick one of these systems, and you'll write a very short proposal telling you what system that you'll end up wanting to write, or wanting to model. You'll give a presentation that of your results from the model and what conclusions you've drawn from the model, and you'll submit a report. And so that will be mostly concentrated towards the end of the semester. I'll prompt you for all of the deliverables, so you can start thinking about how you want to form your teams, but you don't actually have to formally form your teams until much closer to, say, spring break. And all of those dates are on campus. I think Canvas, all of the assignments I think are out there. I think there might be some massaging I have to do, some lectures and some wording, but I think generally almost everything, if not everything, is already up on Canvas. So you should see a complete calendar of things that are deliverable throughout the semester. So relatively simple plus-minus grading scale. So that's kind of like a lot of the general structure of things. Are there any questions? As I wait for questions, I want to point out that I do this thing where I've got this QR code here and this URL. So right now there's a Meeting Pulse link that's linked to this one here. And so a lot of people have a question, but they just don't really want to raise their hand. And so if you were to visit this QR code or this URL here, which is just bit.ly/212questions, you can submit a question and you can vote on other people's questions. And I'm just hoping everybody's being an adult and as they're submitting these things and for this open forum. And if we hit particular lulls in the class, I'll try to take a look at those during class. But if I miss some of those questions, then in the discussions boards on Canvas, I'll go and answer them on there. So if there's really something you sort of need a clarification on, but you don't want to speak up in class, this is an option. So every question slide that I put up will have this here as a reminder, and you can use the computers there, or you can use your mobile phones and do that. So with that, are there any questions on the structure of the class, what's expected, the deliverables? All right, so there's a couple other administrative things that I have to go over. So most of this is in detail in the syllabus, which is linked on Canvas. There's this academic integrity kind of quiz that's up online that everybody should complete by, I think it's by Sunday, I think is the due date there, but that's all up there. So in order for you to get access to the rest of the course, you should complete that. It's due basically at the end of this week. For Title IX, they sort of stress that I'm supposed to remind you that if you do ever come to an instructor like me, or anybody, any employee of the university to report that you've seen harassment or some sort of sexual or otherwise, that we are mandated reporters, and so I have to report it up through a particular chain, and that's fine. It's not to dissuade you, but it's just to remind you that I can't keep anything like that confidential. So if for some reason, I don't want to put together scenarios of why, group work or whatever, but if for some reason that comes up and you'd like to report it to me, just keep in mind that I have to report it as well. So other things, late policies, basically I think this is kind of common Swiss sense, but there's, I've got these drop policies on the assignments, and otherwise there's no specific late policy, so just turn everything in on time. If there is something that comes up that's, fits in the excused absence category, like a medical thing, then let me know ahead of time if possible. If it is a medical thing, an emergency, let me know as soon as you're well enough to let me know. So the end of the semester isn't the time to say, oh, I missed that assignment back in the second week, I just forgot to tell you, if I could get credit for that assignment, then I could bump my grade up a little bit, so could you just take care of that now? So that, make sure you tell me that as soon as possible. So that's all I'm kind of saying here. Academic integrity, the big thing I want to stress here is that you'll get a lot of material, digital material here. Don't post it on online websites. If you go looking for that stuff, don't share it with others outside the class. Basic stuff that even if it's your own handwritten notes, ASU's policy is your own handwritten notes you're actually not even supposed to post, even though that's your copyright because you wrote it. It violates academic integrity to sort of say, well, I wrote out a solution for a particular homework set and then I posted my written out solution. So don't do that sort of stuff. Again, I hope this is sort of common sense, and all this is kind of up on the syllabus. Otherwise, again, this is just kind of standard boilerplate stuff about what will happen if anything goes crazy in the class. So any further questions about this structural stuff before we get into more content? All right, so the basic schedule, topic schedule, is this week. We're going to start out under an introduction to simulation modeling. So this is going to be very high level and sometimes kind of philosophical. And then we'll transition to these things called causal loop diagrams, which aren't as mathematical, but they start just outlining the structure of these systems that we will ultimately want to model, looking for feedback loops, trying to understand those feedbacks. How many of you have taken systems thinking? All right, so some of this stuff should feel like it overlaps with systems thinking a little bit. If you talk about positive feedbacks and vicious cycles and these sorts of things, what we're trying to do in this course is take those same sort of insights. If you haven't taken systems thinking, that's fine, but take the conceptual insights, the qualitative insights you get out of a systems thinking course and make them more quantitative so you can actually make predictions that are a little less hand-wavy and a little more data-driven. So we'll move from those causal loop diagrams, and that's when we actually start simulating stuff, and that's where we introduce these stock and flow diagrams. That's kind of the basics, and so that's when we'll have the midterm, and that midterm will also have that retake, keep in mind. And then we'll go on to more advanced stuff, and so we're going to take all of the modeling that we did pre-midterm, and we're going to start applying it to different types of models, making our models more complicated or more complex, adding other components, showing us other things that the tool can do beyond the very basics. And that kind of covers up stuff here. And then we'll close, and I think time will permit for us to talk about really sophisticated and trendy topics like chaos theory and things like that. The models that you will simulate can actually manifest these things that you might have heard about in sci-fi, like chaos. We'll say, well, what is chaos? And what is a tipping point? People write whole books, best-selling books on tipping points. We'll formally define what a tipping point is and show how your models can exhibit those and why that's a good thing or a bad thing, and those sorts of things. And so we've got a couple other advanced things that we'll cover as well there. And then we'll have these final project presentations. So in a class size like this, rather than us all presenting to each other within the class, and this is something that I did in another simulation course, and it worked out really well, so I'm going to try it in this course. Your groups will actually not present up here. What you'll do is you'll present in the comfort of your own homes as a video presentation. It could just be slides with audio. It could be however you think best captures that. And I think we'll say later, but I think it's about a 12-minute presentation. You'll upload those to Canvas, and then not only will I watch that in the TA, but what you'll do is that each individual, after everybody uploads their presentation, each individual one of you will be assigned one for you to do a peer review of. And so then you'll watch that and then use Canvas to peer review with a rubric and then give sort of a constructive comment on that. So then what your grade for the presentation will be in part the reflections that your peers have, the aggregated scores of your peers combined with my evaluation and the TA's evaluation, and that will be sort of your presentation score, but you'll also get a small peer evaluation score, and that will be, does it look like you put some thought into this peer review? So I basically go through and did they do the rubric? Yes, and did they leave some thoughtful feedback? Great. If they did, then that's when you get your point for the peer review. So that's a way that will hopefully make it a little more convenient for you guys. That way you don't have to sit through everyone's presentation, but your own presentation is guaranteed to probably get, I haven't done the math, but let's say 3 or 4 different student views and then the views of the instructors. So I find that, I think usually students find that it's a little more flexible and you don't have to worry about the audience anxiety issues, and then it gives us more time in class to actually do work on the projects, like in open labs and things like that. So any questions about that structure? And then of course the final exam, and I explain the retake. We'll do 1 try during the last day of the class. And then if you come back for the final exam, we'll only spend 75 minutes of the final exam period because those 2 exams will be kind of similar in length. So any questions about that structure? Yeah?
Will the exams be, will they use like theoretical questions, or will we be using modeling software?
Oh, good.
Computers?
Excellent question. So your opportunity to demonstrate to me that you know how to use the software will primarily come through your final project. So the final project is kind of like it takes the place of the second midterm. So the final exam will more be conceptual. I still will leave things open for saying, like, in Vinson, if you wanted to do X, where would you find it? I might ask you that sort of question. But it's not a practical exam. So we won't have you open up things on your computer, build things, and then have us look around and see if you implemented something correctly. Does that answer your question? Any other questions? Okay. So if you were to go to the sustainability website, there's a what you will learn, and if you click on that what you will learn, there are these so-called core sustainability competencies. And there are systems thinking, futures thinking, values thinking, strategic thinking, and collaborative competency. And they define what each one of these things mean. And this has come to become a metric on which all sustainability programs are measured. And so it's my claim that we touch on 4 of the 5 of these all in this course. And so, so that's kind of how we're going to use this tool. And so this tool is not only allowing us to say, think about a particular system, but even communicate, so collaborative competency, ideas that are difficult for us to get out of our head. And so we instantiate those ideas in a computer model that we can then show to others. And so part of this course is about simulating systems, but another part of this course is about using numerical simulations to communicate ideas that would be otherwise difficult to communicate if you were just verbally. So, so that's kind of where this kind of comes up. So, so basically, in order to get into what is a model and what are we going to do here? So, a lot of people is kind of concentrating on this. What is a model here? So, I'm showing up here 3 different things that can be called models, and it's my claim that these 3 different expressions are all actually identical versions of what's called an SIR model in epidemiology. So we'll learn about these in a little more detail later in the semester, but basically this SIR are these susceptible, infectious, recovered. So this is what they call a 3-compartment model, which represents a population of people who are either sick, contagious, or not sick. And so then you're interested in, given that everybody starts not sick except for a couple of them, how quickly does everyone get sick? Or is it possible for those that are sick to actually end up becoming recovered before everyone gets sick? So it's a way of studying dynamics of the spread of disease in a population. And mathematicians like to draw these these expressions here, which are these coupled differential equations. So whenever you see a variable with a dot over it, that is a notation which is shorthand for ds dt, or d, whatever the variable is, dt. And so I won't go into a lot of details here, but basically the right-hand sides of these equations have to do with how quickly do people transition out of being, say, susceptible to a disease based on how many other people in the population are susceptible and infectious. And so you can see that in order for the total number of susceptibles to decrease, that's why there's a negative there, a susceptible has to bump into an infectious individual. So the product of the number of susceptibles and the number of infectious apparently has to do with the rate of transition out of here. So I've just described something like two people bumping into each other, but I've coarsened over that and just said, I don't actually care about the people, I just care about how many of them are in these three bins. And so I could have drawn this graphically in this form here, and this is a so-called stock and flow diagram. These are the diagrams you're going to learn to draw in this course. So instead of writing these formulas up here, you end up formulating this thing down here. So 3 categories of people. S, susceptibles, I, infectious, R, recovered. There are 3 little boxes there. They flow into each other. A susceptible becomes infected at a particular rate, and this is like a valve that's turning a rate. And then those infectious become recovered at a particular rate, and this is a valve which affects the rate. And these rates are affected by the number of people currently in the bins. So this graphical expression represents everything that's written up here, but to me, this actually communicates the idea much better. And we'll use tools where you can start with this, and then the computer behind the scenes builds this and does all the math for you. That's where we're going with that. So that's where we're going, but so to ask, what do we mean by what is a model, and why do we call these things models? Why would we bother to do this to begin with? So there are kind of 2 categories of models. You hear people talk about mathematical models like those, and then these computational models. So these are models where you don't end up solving them with a lot of math. And they're both types of models. But what is a model? So these are fashion models. So why do we call them fashion models? Does somebody have an answer to that? Why are they models? Why are these, what gives us the right to call these models? Yeah.
They represent perceived market standards.
So that's an interesting point. That is almost always the first answer I get when I ask that question. So that answer was they represent our maybe perceived, our norms, our normative standards of what people should look like. And that is, I think, what these have become. They are models for what we maybe want to look like or what we think others want us to look like. But is that why they started that way? Did we initially we called these people fashion models, like before the kind of fashion models, before the tail started to wag the dog, there was a time when the dog was wagging the tail. So why, more fundamentally do we call them fashion models? Yeah? Exactly, right, they're presenting a product. So in this case, she maybe is modeling the red dress. He's maybe modeling, I don't know, the jacket or maybe the whole outfit. So the idea is that without her figure and without his figure, if I was contemplating maybe purchasing one of these 2 things, then it might be difficult for me to really answer the question, what if I put on those clothes? So if this was just hanging on a rack, or this was just hanging on a rack, I might want to try them on myself, but if I don't have the ability to try them on myself, this is the next best thing. It starts answering this what if question. Now, back to the normative thing. There's a lot of degrees of freedom here. So somebody who's selling this dress might say, well, yeah, I want the person to better understand what the dress might look like on her, but I don't just want any average, figure behind there. I would like people to be distracted by additional degrees of freedom that I have control over. So I am not going to just choose any average person. I'm going to choose a person that I think will be viewed as attractive by a large portion of my demographic. And that may have been done intentionally in many of these cases in fashion models. But we have the ability to accidentally do that when we build computational models. So when we build models, mathematical models or whatever, these are maybe the things we're trying to answer questions about. And these together are the computational systems we're trying to use to answer those questions. But what we fit into our dresses are our assumptions. And we are making certain assumptions here. Like, let's look at this guy, for example. I've lost a lot of weight recently, but I still am not at his proportions. I might look at that. I probably don't put enough, the same amount of product in my hair in a week that he has in his hair right now. You know, but I might look at the way he's looking, and they're all for some reason bent in the same way, which is also kind of weird to me. So it might be that if he stood up straight, he put on a couple of pounds, we combed out his hair, then suddenly this outfit doesn't look so great. It might be it still looks good, but you put it on me and it just looks terrible. Maybe I'm just, horizontal stripes aren't a thing for me. So we have to be careful about the assumptions we do when we do our modeling. And so that's totally reasonable to call these models, and we want to make sure that our models say fashion models for the old reasons and not for the new reasons. All right, so similarly, why is this, my biological friends call an animal model? So it's a mouse. You can see it's being held by a gloved hand, so maybe in a laboratory situation. So this is like a mouse in a laboratory. Why might we call this an animal model?
The same basis for different tests.
What do you mean by the same basis for different tests?
It's the constant when you're working through whatever system you're doing, so you can keep putting different changes to it so that you can find what the outcomes are.
Well, can you give me an example of how that applies to the mouse in particular? Do you have like a particular
say you're doing cancer research and you're
okay.
looking at what certain things cause cancer in certain products.
Oh, okay. So you're
instead of a human, this is like.
And so instead of a human, I use the mouse.
Yeah.
Right. So ultimately, the what if question is, what if I used this particular drug on a human? But maybe I'm not able to get access to humans. Maybe it's not ethical for me to use humans. But for whatever reason, society has deemed that it is ethical to try those things out on mice. Now maybe the mouse model, for most of the physiology I care about, is close enough to the human model that if in the case of cancer, maybe I've given this mouse cancer and I want to treat the cancer. If I'm able to treat the cancer in a mouse, maybe I then make the jump to say, well, maybe then it'll treat it in a human as well. And so that's where, this is an animal model because it is a stand-in for a human to ask the what if question of what if I use this drug on a human. Now, again, just like in the fashion model case, there are some assumptions here. Like this mouse has a long tail. I don't have a long tail. This mouse has a lot of hair. I don't quite have that amount of hair. This mouse has to chew on things to keep its teeth from growing too, I don't have to worry about that. So there are clear differences. And yet, we use them because they're better than nothing. And then we likely build on these models to move to the next model and the next model. So a model, again, I'm trying to just drive home this, is helping to answer this what if question. Now, in these mathematical models, this is not a population of sick people. These are just 3 equations. Way oversimplified. If somebody's sick, they cough, you might stay away from them. So, how does that capture in this model? It may not be. But what's nice about this model is that if you can say this is better than nothing, you can use the math that you learned in SOS 211, or maybe a little more advanced than that, to then provide answers. And those answers will be in terms of all these parameters which are interpretable. So it gives us knowledge that we did not have without the model. Down here in our computational models, we get rid of these, or I'm calling these empirical models, is that instead of solving them, we just run them as if they are the mice in our laboratory. So this is our mouse. And we are going to, just like we inject the mouse with some drug and then see what the outcome will be, we will inject our computational models with different conditions before we try the conditions in the real world. And we will see what happens to those conditions here by experimenting with the computational model. That's what we're kind of doing here. So when you see this, you should think this, because this is an experimental model, just like this is an experimental model. So they're all the same, they're all models, and they're all trying to answer these what-if questions. So that could be a midterm question, because what the most general definition of what a term model is it answers a what-if question. It doesn't have to be mathematical. It doesn't have to involve a computer. It doesn't have to involve a mouse. But It's totally accurate to call her a model, just as totally accurate to call the mouse a model, the computational model a model, and even the mathematics of a model. And what I hope that you'll start seeing is if you start looking at the world through this lens, then there's a bunch of other models where you might start questioning the assumptions you're making about reality in general. Up here, I have 4 different models of an electron. So we have the Bohr model of an atom, suggested that an atom had a nucleus and it had these electrons that orbited in these circles. And for a while, that model did a pretty good job predicting the properties of matter. You could go and you could say, if underneath it all, we assume that matter is organized this way, we would predict certain macroscopic properties that we could test. And lo and behold, in the laboratory, those properties hold up. So this ends up being a good conceptual tool to ask, if I were to build something of a particular structure with particular types of materials, how would it behave? And this would tell you how it behaves, so you could go ahead and build it and feel pretty confident that it would behave like you predicted. But it turns out in the laboratory that worked so well that at a particular level of precision, this model failed. And so a lot of people don't know about it, but Bohr, when he came up with this model of the atom and realized these failures, reconceptualized kind of like the way we think of our solar system in terms of ellipses. He said, well, what if the electrons aren't moving around in circles? What if they're moving around in these ellipses? And if you use this model of an atom, which he tried for a while, you can improve upon those predictions, but only up until you can't. So it gets a little better, but it still ends up failing at certain things. So, but you can kind of see how you could evolve from here to there. But eventually you get into things that you might see in maybe a maybe a first chemistry course or second chemistry course in college, and you learn about molecular orbital theory and stuff like that. And now your electrons are these clouds, and they don't look at all like this. But this is so much better at predicting the properties of matter. So for, 75 years, 100 years, these are the electrons. And then suddenly, these are the electrons. They're totally different. And then over here, you have the so-called standard model of particle physics, where the electron shows up. But it's not really looking to answer the same questions as this model over here. So these two kind of coexist, and they're consistent with each other, but they don't necessarily build on each other. And so the point I'm trying to drive home here is that electrons do not exist. They're models to help us make sense of the world that I'm walking on, the fact that I'm not falling through the floor. But I have no reason to believe the floor is actually made of electrons. All I can say is that electrons are a useful concept that has been shown over time and time again that it's preventing me from falling through the floor. And likewise, we are going to find that our computational models, we do not need our computational models to be so accurate that we can say that we've got every single thing right. But we do need to show that we're able to make predictions that hold up in real life that are better than the predictions we could have made without the model. And if that's the case, then our computational model, although it may not be accurate, whatever that means, it's still useful. So there was this George Box, there's this quote, and I hate putting up old white guys, even though I will someday become an old white guy, but unfortunately, most of the other old white guys before me quote on the other old white guys. So there are plenty of other quotes, but this is one that I'm sure a lot of you have heard. All models are wrong, but some are useful. And so George Box said this, and I think a lot of people, when they hear it, think it's a criticism of models. But that's not what Box was saying. He was saying here is that we shouldn't be asking if a model is right or wrong. We should be asking how useful it is. The practical question is, how wrong does a model have to be before it is not useful? And so we are never ever looking to build correct models. We're always looking to build useful models. And so he went on in a different text to say, for a model, there's no need to ask the question, is the model true? If truth is to be the whole truth, the answer must be no. The only question of interest is the model illuminating and useful? So there's going to be criticisms. Initially, I hope when you're building your own models, you feel the internal criticisms of your own models to say, I'm not sure I got this quite right. And then when you present it to other people, they're going to then say to you, but you said that when people bump into each other when they're sick, that this happens. And I'm not sure that always happens. It might happen 90% of the time, but what about those 10% of the time where that doesn't happen? And you have to push that away. And you have to say, if I were to make my model more complicated, would it actually provide better predictions than it already does? And if it wouldn't, then it might be better to keep it simpler. And so ultimately, the metric you should be using is it illuminating and useful, not is it correct. So I saw this fortune cookie once while I was teaching this course, and I thought it was a nice coincidence. Do not seek to find the answer so much as understand the question better. And I think that's all of science. And so we're not looking to find the accurate model, we're just trying to find the next model of the electron. Because for all you know, there's a graduate student that is 2 blocks away from here in a laboratory working on her own experiments with fundamental properties of matter, and she will find that there will be some property that she just cannot understand or predict with molecular orbital theory, and will come up with a totally new theory of matter that may not even have electrons in it. And at that point, do we say that electrons disappeared? I mean, with Newton, gravity totally changed going from Newton to Einstein. But the underlying physical reality didn't change, just the way in which we were making predictions on it. So ultimately, we're not looking to find truth, just finding tools to make sense of the world around us. So with that, just give you a more concrete example of what we'll be doing this semester. For one, are there any conflicts with what I just said? Questions, comments? Yeah.
So like when we do the modeling, is it similar to like system thinking where there's just like using equations to create like causal loop diagrams and not like change over time? Is that like what we're looking at?
Absolutely, yeah, that's what we'll get. So we sort of start with causal loop diagrams, and instead of building equations, we use these software tools that hopefully allow us to do more than you could if you were actually manually writing the equations. So we're not going to write a logistic equation for logistic growth. We'll build a much more complicated diagram, something like this, where it'd be, if you were to write this in terms of a differential equation, it might have 15 variables in it. But we won't write the 15 variables. We'll draw, effectively, we're drawing like a causal loop diagram. We're going to add dynamics graphically to it, and then let the computer unroll it. But the essence of what we're doing is exactly what you said. Identify the causal loops, add dynamics, and then unroll that and see how things perform over time. Any other questions? All right, so I like this example. So if I click down here, it will. So this tool that I'm bringing up here is called Insight Maker, and it is one of the tools that we'll learn to use here. And so this is this bird feeder dilemma problem where it's actually difficult to read, so I'll kind of read this out here as I click through this. But this is also something that's linked from the slides if you were to do this on your own. But so basically this is something that somebody notices that whenever he sees birds outside, that creates a pleasant morning for that person. And so that person, you think, well, that indicates to me that maybe I would like to have more birds. And so when you look outside and you see that you want, that the birds are giving you a pleasant feeling, you put up a bird feeder. And that's nice because initially you get more birds. But then you realize that that bird feeder is going to need bird feed in order to work. So, so that's great. So initially I put up a bird feeder, and that increases the number of birds. So I'm gradually building causal relationships here. So you can't read this. Birds outside at breakfast create a pleasant morning. A pleasant morning encourages me to make a bird feeder, and that bird feeder increases the number of birds at the feeder, which hopefully then increases how satisfied I am. So that improves my morning. But the downside of a bird feeder is that it also increases the attractiveness of the garden, which adds to that. But the downside of having a bird feeder is that jumping ahead. The pleasant morning takes away from my frustration, and if I had a lot of frustration, that would distract me from my pleasant morning. So as you get more and more of a pleasant morning, then it actually builds upon itself. But the downside of all of this stuff is that your bird feeder is going to require you to buy bird seed. It's going to increase the spillage of bird seed, and that's going to make you have to buy even more bird seed to deal with the spillage, and that is going to add to your frustration. And so you can see how this keeps going on, and if you include, there's squirrels that come involved and bird poop, and once you add in all of the different aspects of the system, it becomes less clear that it was a good idea to pursue getting a bird feeder. So this is something that we're going to try to understand in this class, is how do we build quantitative models to address questions like, should I buy a bird feeder? And if we outline all of the different causal relationships, we can hopefully then use computational tools to weigh whether the benefits of adding this bird feeder, given the systematic effects, are going to outweigh the costs of adding this bird feeder. That numerical problem of do the benefits outweigh the costs is very difficult for our heads to do, but we lean on the computational tools to do that mathing for us, to weigh those two things against each other. To make that a little more concrete, I'll flip to a more dynamical example of these moose and wolves, a predator-prey example. I'll see if I can zoom in here. So maybe I'll stop. Oh, that's big and that's good. So here is an example where we're drawing stock and flow diagrams, which for now are sort of more complex versions of these causal loop diagrams. And we can say that we know that moose, they are born and they die, and their death rate is determined by some factors that we can parameterize, and their birth rate is determined by some parameters. And we'd say, does this model the entire system, everything of importance to moose in a population? And I can take this and behind the scenes build a differential equation and unroll that differential equation and plot it over time. And this is what Insight Maker will do for you. As you're drawing these things, you don't realize it, but you're actually writing a differential equation. And then you can tell Insight Maker to integrate that differential equation, and it gives you these plots. And it shows you the moose population is in green, and then it's got deaths. Moose deaths are going up as the population is going up, but the births are going up faster than that. And so you get this growth, and this growth appears to grow forever. And we know that exponential growth like this can't go on forever, so we're apparently missing something. So we could say, well, maybe one of the key things we're missing are predators, and so I'm going to add wolves in. So I've got wolves, and it looks exactly like the same system. I've got a wolf birth rate and a wolf death rate. If I don't include the moose in that, then my wolves are going to start at some initial population, and they're going to end up dying out. And that's what we're seeing here, this wolf population dying out. So if I couple those two things together, I think, well, this is going to be great. If I couple the moose and the wolves together, so that now, if there's more moose, I get more of a wolf birth rate. But as I get more wolves, I get more of a moose death rate. So these things are all coupled. I might think I'm going to stabilize the population of both at a constant level. And so that's what I might think just doing a pen and paper solution. But if I use the numerical tools, I can actually simulate what happens. And under these conditions, then what I see is something that might have been counterintuitive, is that I get oscillations where the moose population starts low, it gets high, and then it goes through cycles. And the wolf population goes through similar but shifted cycles. And so what I'm actually seeing here, now that I see the graph, it all makes sense. I see that as I get more and more moose, that's going to increase the birth rate of the wolves. So I'll get more and more wolves. But once I have a huge number of wolves, that's going to cause the death rate of the moose to skyrocket, causing the moose to plummet. But as the moose go away, the foods for the wolves go away, which will cause the wolves to come down. So I can see that there are conditions that I can set that will cause these two populations to constantly be cycling. And if you go into nature, there are a bunch of systems that actually act a lot like this. So there's fish in this famous lake in Africa that their mouths, they have populations where their mouths are on the left or the right, and they eat scales off of other fish. And based on the number of fish that are right mouth, then the fish that they prey upon learn to kind of immediately turn left whenever they feel any sort of disturbance, and that scares the fish away. So once the other prey fish doing a lot of turn left, that gives an advantage to the fish with the other mouth. And you actually can watch these two cycle back and forth. So if you just sample the lake at any instant of time, you get one snapshot of the population, you might think that's the population at steady state. But in reality, these two numbers are going back and forth, which is why you may have to sample the population over time. And this gives us an idea of the causal forces that might be behind that. So that's kind of the general idea here, is can we build systems where we can't challenge any of these links, but when we put them together, we get trajectories that come out that we might not have been able to predict without the models. But then once we see the trajectories, it gives us totally new insight into how these things come together. And so that's where we'll be, hopefully, by the end of the semester, is that you'll feel comfortable taking these causal relationships that you think you can defend to someone, putting them all together in a way you can defend, and then let the computer unroll that argument so that you don't have to defend it, because it's just a natural outcome of the links, which everyone has already accepted. So that's kind of where we're going. So let's go back in here. So any questions about any of that? Again, you're not supposed to totally understand that now, just giving you a snapshot of where we're going. And we're going to start at square one with the causal loop diagrams and an introduction to modeling as we move on through the rest of this week and next week. Questions? All right, well, I don't think there's a lot of other stuff that I have here. The announcements I have here is that you should gain access to the Moorcroft textbook. Remember, it's available for free online. You can get a link on Canvas to chapter 1 or to the whole textbook. And I mention that because there is, I think it's lecture A3. It'll stay online. I think it's going to be like a week, maybe from today, where we'll have our first assessment. So read chapter 1 and answer the reading exercise. The due dates are online. You should, whenever you've got a convenient time, it might be useful for you to download BinSim on your own computers. We should have them on the local computers here, so we can do the work in class. But if you want to continue to do this work, then it will be easier if you have a copy of BinSim. It's freely available, and there's instructions online if you're having trouble with it. And then eventually we'll need Insight Maker. And so it's a good idea to do that now. You can create a free account at insightmaker.com so you can start using that tool. Any questions about this? The upcoming assignments. So Sunday night, that's that reading exercise over the syllabus and the academic integrity. You can do that assignment as many times as you like. We'll take the highest score, but you have to get a perfect score to unlock the rest of the course. There's a muddiest point due Sunday night, so over this lecture and next lecture, you just sort of say what were the clearest point, the muddiest point, anything interesting. And then there's this assignment A2 that we'll start next lecture, and we'll start working on in class. So start reading chapter 1. There again by A3, which will be a week from today, that's when we'll have our first in-class assessment. And due the day before that, Monday night, there'll be an at-home reading exercise. It's meant to help guide you through the kind of highlights of the chapters so everybody's reading the same parts or the right parts. So if the last thing that I have to do, as I mentioned, I'll take attendance. And the way I do that is, again, using one of this online things. So there's a Google form attached to this link. So if everybody right now was either you can use your phones or the computers in front of you, or if you like, you can just submit to me a piece of paper filled out this way. But of course, it's convenient just to do it this way. And basically, what I do is you'll go to this and it'll say, like, what's the answer to your question? So I ask you a question, and I might do this in the middle of the lecture as well, and you fill out that, and by the end of the class, you hit submit with whatever answers have accumulated throughout the course. I don't grade them for correctness, I just grade them for completion. So for now, I just want to ask you guys, what is the question that a model answers? So I said our general definition of a model is it answers this type of question. So what was the type of question? So if you go to this link, under like, it says like question 1, 2, 3, just under question 1, put your answer to that. So what question does a model answer? So I said a model is defined as something that helps us answer this type of question. What is that type of question? And then that's all that I've got for you today. Yeah, question?
So, do you like, so once we answer the question,
You
do
can
you want us
see
to put, oh, okay.
Yeah,
You don't
just-
need to worry about like the last 4 digits of.
Oh, no, this is, if you do not have a computer or mobile device, submit a paper response of this, and this just helps me sort them, and so I can have the grade. I used to do this all in paper, but now I primarily do it electronically.
Wait,
10 questions.
there's 10
It
questions.
was 10 options. So this is just a generic form. So I only asked you one question today. I potentially could have asked you 10.
10, okay, so we just submit one answer.
That's right. This
Alright,
question
got it.
one, put your answer to this. And then I'm going to try every lecture to record the lectures and put them online. So I've got a video recording, a recording at the here, and then also an audio recording. So I'll post those on Canvas. So if you miss anything and you feel like it's useful, or if you have to miss a class, then those should usually be posted online within a day of the lecture. So otherwise, I'll see you guys Thursday.